So for example, you are bungee jumping. How I wish I could bungee jump right now. Okay. So because of the size of the person like this, there are two forces acting on the person. That includes the downward force due to gravity, wherein the magnitude is equal to mg, and there is an upward force due to the air resistance. And we call this your upward force, and this is your downward force. And let's say that upward force is directly proportional to the square of the speed, and the direction is opposite. So if the person falls down, so the direction of the upward force will be upward, and the proportionality constant is defined as the drag coefficient. Okay, it is called the lump drag coefficient because this is basically includes or dependent on the surface area, the density, and everything about that person. Okay, excluding his personality. Okay, m is the mass of the jumper, and g is your usual acceleration due to gravity. Okay, so this is your problem. So usually when we solve this problem, what do? Is we solve this using Newton's laws, wherein the sum of forces acting on the particle, which is, so let's say we set the downward direction to be positive, so that the sum of forces will be mg minus cd d squared. Okay, and by Newton's laws, this is equal to the mass times the acceleration of the person. Okay, and we know that acceleration is the derivative of the mass of the velocity with respect to time. So, and then dividing everything with mass. So we end up with this differential equation. The derivative of the velocity with respect to time is equal to g minus cd over m, which is a factor, which is a constant, times v squared. So this is your differential equation. Okay, and let's try to solve this differential equation using your symbolic math. Okay, so let's have a new script. And let's solve this differential equation. Okay. So of course we want to, wait. Okay, so let's do the symbolic math first. So sames, and our variables will be g, c, m, and then v will be a function of time. And then let's say when you bungee jump, your initial velocity, in v at time equal to 0 is equal to 0. And then we define our differential equation dv dt as the derivative of velocity with respect to time. And that is equal to g minus c. Let's call c to be our cd. Or c na lang. Sige, c na lang. To be our drag coefficient or lump drag coefficient. And then times v squared. Then divided by the mass of the particle. Okay, so let's try to run this first before solving it. So just to verify, I'm sorry, should not omit this. Okay, so this is your differential equation, which is the same as this one. Okay, now, can somebody tell me how to solve this differential equation? Let's say the solution would be equal to SOL. Anyone?
Dissolve, sir.
Okay, dissolve. Ano, what's next?
DVDT.
dvdt. What's next?
Initial conditions.
Okay. Let's solve. And as you will notice that it is a very complicated solution. Okay. So if you're going, if for example, if you do not have your computer right now, and you do not have MATLAB, then you just want to solve this algebra by hand, you'll end up with this solution. Okay. So we can see that the solution will be v as a function of time will be equal to square root of g. Okay. Yeah, okay. Square root of g m over cd times the hyperbolic tangent of square root of cd g over mt. So this is the solution to this differential equation. Okay, and let's see how are we going to let's say let's plot this. So let's say f plot. Okay. And then let's say let's run. Okay, so may mali. Okay. So this is our solution, and let's say f plot must be a function. So anyway, so this is your function. So how do we define our function? Anyone? Okay, so if we're going to solve this, okay, what we can do is we can actually plot this by plotting time versus velocity versus time. Okay, anyone? Ano ba? Ano ba? Okay, so let's do this. Okay, so let's do this like this. So let's say from 0 to so let's say we solve this by setting first our function, our time axis. So let's say this is from 0 to 12 with intervals of, let's say, 0.1 time axis. And then let's define the velocity to be velocity function this time. So square root of e times m divided by c times hyperbolic tangent of square root of c times g divided by m, m times time. In this case, let's define our constants. G is equal to 9.81 m, and let's say n is, okay, we will use the, let's say 68.1 kilograms. And then CD or C is equal to 0.25. You'll notice that the constant it has a unit of kilogram per meter. This is meter per second squared. Okay, and then let's do the plot. So this is time, and then let's see. Okay, so this is your graph. Okay, and then let's do some labeling. X label is V as a function of time. And then T. The unit is meters. Time in seconds. And that's 1. Okay. And let's run it again. Oh, sorry. Should be this one. Okay, sorry about that. Should be Y. And this X label. E Y label. Oh, sorry. Wrong. Okay. So let's copy output. And then let's try to save it here. Okay. This is the sorry. This is the output. Okay, so we call this output the analytical solution. So this is your sometimes we call this your exact solution. This one. Okay, and this is the graph of your function. Okay, so we know exactly that the velocity function follows this graph. Okay,